Good morning, everyone. In this session, we are going to see the next topic in our digital electronics subject. The topics covered under in this session is number system conversions. Under number system conversions, we are going to see different types of numbers. Those are decimal number system, binary number system, octal number system, hexadecimal number system, and relationship between numbers and these conversions. Let's get into our topic. So in number systems, we have different types of numbers like decimal number system, binary number system, octal number system, and hexadecimal number system. Under decimal number system, it is of base 10, which is having 10 different digits ranging from 0 to 9. Ranging from 0 to 9. So in decimal number system, it's a positional value system. Why? Because we are calling it as positional value system. Each digit contains one positional value to it. For example, if there is a number called 734. Now in 734, 7 is present in hundreds place and 3 is present in tens place and 4 is present in units place. So units, tens and hundreds. So different positions got a different values. So 10 power 0, 10 power 1, 10 power 2. So these are its weights which are present at a different positions. Similarly, if I am taking any kind of fractional number, it contains a point which is separating decimal part as well as fractional part. That point we are going to call it as decimal point. Now before point, the positional values are represented using positive powers like a normal number, whereas after point the values or positional values are represented using negative powers of 10 in decimal number system. So this is what the difference between a normal number and a fractional number. Next system is binary number system. In binary number system, uh, there is there are only two numbers which are present. Those are 0 and 1. These are called as bits. Now these bits are also represented with positional values only. That is, it is also a positional value system which is represented with its positional values as 2 power 0, 2 power 1, 2 power 2, 2 power 3, so on. And in uh, binary number system, the leftmost bit is called as most significant bit, and whereas rightmost bit is called as least significant bit. Now in similar to that of decimal number system, binary number system is also contains some points in between the numbers. The point we is called as binary point here. Here it is also the leftmost numbers are represented with positive powers of 2 and rightmost power number is represented with negative powers of 2. Similar. Now, if a binary number is represented as 11012 to the base 2, we can get the number in decimal by just multiplying the given base with its respective positional values, so that we are going to get the decimal value. Now, you can see here the first bit, that is 0, is multiplied with 2 power 0 position, next 2 power 1, next to 2 power 2, next 2 power 3, and next 2 power 4 with the given values of the number. We are getting 26 as decimal number. Group of 4 bits in a computer language, we call it as enable, whereas group of 8 bits is called as 1 byte. Like 1 KB is equal to 1024 bytes, 1 MB is equal to 1024 KB, 1 gigabyte is equal to 1024 MB, 1 terabyte is equal to 1024 GB. Next comes the octal number system. Now in octal number system, there are only 8 digits, that is ranging from 0 to 7. Now octal number position is also a positional value system, that is 8 powers are given as its positional values, that is 8 power 0, 8 power 1 to 8 power 2, 8 power 3. Now for example, if there is a number 8231.524, before point positive powers of 8 is represented, after point negative powers of 8 is represented, which is separates, and the point which is separating we call it as octal point. Decimal point, binary point, octal point. Next, in the same similar way, the octal, if the octal number is given, then we should multiply the given number with its positional values to get the decimal value. If 726 is given, multiply with its positional value, we got 470 as decimal value. Hexadecimal number system. In hexadecimal number system, there are total 16 symbols, that is ranging from 0 to 9, where after 9 the numbers are represented, that is 10 is represented with A, 11 with B, 12 with C, 13 with D, 14 with E, and 15 with F. It is also positional value system, that is 16 powers are provided as positional values. Now a point which is separating two numbers, that is decimal part and fractional part, is called hexadecimal point. Now for example, if a number is given as 27FB to the base 16, multiply the given number with its positional values to get the decimal equivalent. So these are different number systems which are frequently used in computers. Let's see the relationship between the numbers. Now for example, if I am having numbers from decimal numbers from 0 to 15, so the same 0 to 15 can be represented in hexadecimal, octal and binary. You can see the representation goes 0 for the same thing. In binary, the decimal number 0 is represented for 4 bit of information, that is a 0 0 0. Now till 7 it is going to be same for everything. Now after 7, you can see in octal system there is no digit called 8. That's the reason I'm making my initial position as 0 and next bit is incremented by 1, and it is 100. Now when coming to the next series of numbers, for a decimal number 10, the hexadecimal representation goes A, and whereas for octal it is 1 2, and it is 1010 in binary number system. So this is how the representation goes for all the remaining numbers of number system. Next, we'll see the conversion techniques. In conversion techniques, there are decimal to other number systems. Means if I am converting a given number to octal, hexadecimal or binary, what is the procedure? Let us get into it. Now 43 is given in decimal. We'll see how it can be converted to binary. Now for binary, we are going to use the repeated division technique. Means repeatedly we need to divide the given number for a number with required base. That is 43 is given, so we are going to divide with required base is 2, with we are going to divide it with 2. So 2 divided with 43, that is 21 times, remainder is 1. Now 2 divided with 21 is 10 times, that is remainder is 1. Again 2 divided with 5, remainder is 0. Next 2 2s are 4, remainder is 1. Next 2 1s are 2, remainder is 1 0. Next 2 1s is 1, it is not divisible, so 1 I am taking directly. So 1 0 1 0 1 1 is the binary equivalent for 43. That is, I need to collect all the reminders in the reverse order. Similarly, if there is any fractional part, that is 152.25 to the base 10, can also be converted by just dividing the given number into two parts, decimal part separately and fractional part separately. That is 152 plus 0.25 will give us 152.25. Now in normal way, 152 is divided with 2 continuously. So I got this number. Next, for 0.25, we are going to multiply with the required base. So multiply 0.25 into 2 times. That is we are going to get 0.5. So separate fractional part, decimal part here separately. If I am separating my decimal part, it is 0 here, and fractional part will be 0.5. Again multiply 0.5 with 2, you are going to get 1. So decimal part will be 1, fractional part will be 0. Now 0 and 1 is the binary equivalent for my 0.25. So 0.25 decimal part is equivalent to 0.01 as its value. So the final value will be 152 plus 0.25, that is 1001100.01 is the binary equivalent for my given number. Similarly, now if I am having decimal to octal conversion, now decimal to octal also is the same way, where 8 is the given number required base for given decimal number. So 473 is divided with 8. Again collect similarly the all the reminders the which are existed with the 8 division. Now when I divided 473 with 8, I got reminders as 731. So 731 is the required octal number. Next, similarly 152.25, divide the number. 0.25 will be the fractional part, 152 is the decimal part. When divided with 152 8, you are going to get um, 230 as the required answer. For 0.25, you multiply with 8 here. Now when multiplied with 0.25, 8, the resultant is 2. So zero point 0.2 is the required answer for 0.25. So 0.25 into 8 gives me 2. So final answer is 230.2. Now when I am converting my decimal number to hexadecimal, divide with 16. When I am dividing with 16, you are going to get 1a7. A means 10. So when remainder is 10, I am representing it with a. So that is 1a7, 16 to the base 16. Now 152.25 similarly. Now 152 I will divide with 16. I am going to get 98. And for 0.25 you multiply with 16. We will get resultant as 4. So the answer will be 98.4. These are the number conversions to the decimal system. Now we'll see the other way, binary to others. So binary to decimal, if I wanted to convert to binary to decimal, just multiply the given number with its positional values. When you see this particular number, I'm just multiplying my given number with its positional value. So I'm getting my answer as 22.125. So this is how the conversion goes from binary to decimal system. Next come to binary to octal. So when I'm telling binary to octal, it is 2 power 1 is converted to 2 power 3. Means 3 bits in binary represents one digit in octal system. So I'm going to group the given number into 3 bits. Now you can see here the numbers are divided into 3 bits here. Now represent that 3 bits into equivalent octal system. So this is 1015, 2, 6 and 2. So my answer is 2625 to the base 8. Similarly with the point numbers you can do the same thing. Now coming to binary to hexadecimal number system. Binary to hexadecimal system is 2 power 1 is converted to 2 power 4. That is 4 bits are in binary represents one digit in hexadecimal. Now group the given binary into 4 bits. Now when you grouped that thing into 4 bits, you are going to get DB5I to the base 16. Similarly, come for the point values. Next, octal to other numbers. Octal to decimal is just multiply with the given positional values. You are going to get the decimal number system. So multiplying with positional values gives always a decimal number system value. Next, coming to octal to binary. Octal to binary is directly representation of given number using 3 bits in binary. Octal to hexadecimal also the same thing, but a intermediate stage of binary should be obtained. Now here octal to binary is converted, and next that binary is grouped into 3 bits, which is where I am going to get it as an octal number. See, grouping the 3 bits will give me octal number. Next, hexadecimal to other number, that is hexadecimal to decimal, that is multiplying with its positional values will give me a decimal value system. Next, hexadecimal to binary, that is given number is represented with 4 bit of information each, so that we are going to get a hexadecimal number represented in binary, hexadecimal number representing in octal. So that is hexa 2 power 4 16 4 is converted to 2 power 3, that is represent the given number in 4 bits. After representing 4 bits, group into 3 bits, again we are going to get octal numbers. So these are the given conversions for any kind of number. So based upon those numbers, we are representing some of the examples like 1 into 2 power 3, 1 into 2 power 2. You can see here binary to decimal conversion. These are few of the examples. You can go through the examples. Thank you for the session. We'll continue in the next class. Thank you so much.